Video is going to use a quick drawing and some Legos to kind of show a visual perspective of the ambiguous case of the law of signs. And it's going to follow the model that we used the other day. And I think these Lego pieces are going to turn out to be pretty helpful for us in visualizing what we were talking about on Friday. The scenario is as follows. You're asked to build a triangular fence, and you are told that you have one part of the fence that's going to be provided to you by an existing stone wall on your property. That stone wall starts at the left-hand corner of your property, and it runs an indefinite amount off to the right here as we look. This is the beginning of where your stone wall is, and that's where your property ends, so you can't extend any way in this direction. You have to go with your fence in that direction, so keep note of that. We're going to give you two things, and they're seen here in blue. We're going to tell you exactly how long the first part of the remaining pieces of your fence, the remaining two pieces that you have to do to build this triangular fence. We're going to tell you exactly how long it is, and we're also going to tell you what angle that side will make with your stone wall. And we'll call this side B. We'll call the point where the end of this piece that you've been given terminates as point C. So we kind of already have an ABC triangle. B is going to be somewhere along this nice green line. Let's see if I can make this just a little darker real quick if my marker wants to cooperate. Yeah, at least a little bit better. And I know point B is going to exist somewhere down here. Now, the next thing we're told is that we're given a connector. Someone will pretend that someone donated material to us and they gave us a certain length of fence to work with. Will what they give us be enough? It's going to build a triangle, and we're going to call this connector piece. Again, it's going to connect from point C back down to somewhere here on the green. Since it's opposite capital A in our triangle, we'll call the length of this mysterious connector, or this donated connector, A. And so let's walk through the ambiguous case using some Lego pieces. And you'll see I have 3 Legos here of different lengths. 6 blocks, 8 blocks, and then 1, 2, 3, 4, 5, 6, 7, 8. Hey, I can count to 10. How do you like that? A 10 block piece. And so let's look. There's my smallest donated piece. It isn't going to work. It certainly is not long enough. So in this good old ambiguous case scenario, there are going to be cases where my value of A, my donated fence, so to speak, isn't big enough. I can't build the fence. Here's a new piece. It's 8 long, and if you look at it just in terms of how I have the model, it fits essentially perfectly. What we notice is it builds a good old, for me, a nice little right triangle. And so bottom line, in order to even be able to build a fence, I'm going to need, an 8 block piece, at least, a minimum, and then I'll be good to go. And it turns out, if we do a little basic trigonometry, if this is little a right here, the length of this yellow brick, I know the following. I can say that the sine of angle A equals A over B. Now I've kind of measured this, just you notice I wrote B equals 12. I'm just telling you that this length happens to be equivalent to 12 little grid marks on a Lego brick, just for the sake of argument there. Not for argument, but for the actual purposes. In any case, what I can say is, in general, I can build a fence as long as I can connect. The shortest possible would be what? It would run perfectly vertical from point C straight on down to the fence. In other words, it would be a perpendicular. It would create a right angle. It would create a right triangle. This is the minimum possible length that will allow me to construct a fence. And it turns out, again, through some trigonometry, I can simply say sine of angle A is equal to little a over little b, which also says that this minimum length is nothing more than b times the sine of A. Again, sine of A equals A over B, some very, very simple algebra. And this is when I have my right triangle, obviously. All right, so now, let's work with our next piece. Well, first things first, it's too big. In other words, it's not going to create a triangle this way. What am I going to have to do with this? I'm going to need to rotate it. And in so doing, I can build a triangle that looks just like that. And certainly I'd be fine. I'd have a nice, productive triangle for me. But what's interesting is, if I think about it, I could also take this piece, and if I was so inclined and I kind of wanted to make a very tight fence, I could go ahead and rotate it like that. I still have a triangle. It's pretty doggone skinny or whatever, but it's an effective and it's a legitimate triangle. So it turns out, man, I have the way to kind of just rotate my piece, and I can build a couple of triangles. We'll talk about that a little bit more in a second. So what have we seen so far? No triangles. One nice right triangle, slightly longer, two. Now, there's going to be a limit to how often we can pivot both left and right. And I'm going to demonstrate that by this nice little piece. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Hey, I can count to 16. Not only 10, I can go to 16. Let's take a look at this piece. Well, I can certainly do that. I got a pretty doggone big triangle, but it works. And for that matter, if you think about it, remember I said this thing could extend forever, even off the screen to the right. I could get a much bigger piece and still be able to build a triangle. I have no restrictions on being able to, quote, go right. In other words, kind of work this way with my fence. However, if I try to rotate it, what am I going to notice? I'm going to go well past point A. I can't build a fence. Remember, this is the end of my property. It's the end of the stone wall. I don't have no triangle over here. I'm missing a piece. And if you think about it closely enough, what it really translates into, as soon as my connector gets longer than this length of my blue segment, I'm not going to be able to go in this direction. I can build a triangle, certainly, but I only can go this way. And what's that telling me? My one triangle case requires me to go to the right. So that's kind of a quick visual of the law of sines. Can't build one? Can build a lovely right triangle. Minimum length defined right there. B times sine of A. When I get a piece that's a little bit bigger, you can see the red's a little bit bigger. What can I do? I can rotate to the right. I can rotate to the left. I can build two triangles. And I can keep doing that until the point that what? My connector matches the length of side B. What happens then? There's no way I can get a triangle in here. It's hanging off. It's not good. I can certainly go this way as long as I want. And so there's the four conditions for the law of sines. No triangle if my connector is less than B times the sine of A. One beautiful triangle if it's equal exactly to this. Two triangles when B sine A is less than A is less than B. And finally, so there's my two triangles. This is the ambiguous case piece. Two possible triangles. And then finally, one triangle when A is greater than B. So hopefully this visual gives you a better understanding of the concept behind the law of sines. I'm going to do one more piece very quickly. I'm going to look with the triangles that I built here. I'm just going to go ahead and highlight them. This will be a little bit crude. I'm just going to use some of the markings that I already have. There's one triangle, and here is my second triangle. And just another piece that I want you to notice. Two different angles that get created, depending on whether I went right or I went left. My, quote, go right triangle creates a nice little acute angle. My go left triangle creates a very nice obtuse angle, much greater, or at least not much greater, in this example, obviously very much greater than 100, excuse me, much greater than 90 degrees. But the bottom line is, what do we know about these two angles? They are the ones that, hey, remember when you run through and you do the law of sines and then you have to convert an inverse cosine, your calculator, if you can successfully build a triangle, I might add, is going to give you this angle all the time. That's where the answer is. Your calculator is going to give you either the 90-degree version or the go right when you actually can solve something within the context of the law of sines. What it misses is the possibility that you have a second angle if your connector length, your value of A, happens to meet this condition. And one of the nice things, remember, hey, the sine is positive in quadrant 1, acute angle, and in quadrant 2, an obtuse angle. And one of the other things we talked about in class the other day is that the sine of, I'm just going to call any angle, let me use theta, is equal to the sine of 180 minus theta. And one of the nice things is these two angles, we'll find out and we'll show it in 1 second, they are supplemental angles. And let's describe that piece just so you can see it as well. And what we're going to do to accomplish this is come back and use our nice little friend right here. That was our perfect connector. And hopefully one of the things at least you started to get a feel for is that when I rotate this piece, either left or right, the 2 points that I can connect to, they're marked here, are perfectly symmetrical to this. This little perpendicular location, right down from C, is the midpoint of the segment that connects these 2 points on these different triangles together. What's that tell you? Well, if you do a little bit of work, it'll tell you the following. These two angles are equal to each other. Why? Because this little length and this length, here to here, here to there, are equal because this is the midpoint of that segment. What does that tell you? Well, this, whatever value, we'll call this our connector for the moment. Whatever letter we call this, let's just call it H for the second. I know that what? The sine of this angle, excuse me, the cosine of this angle is equal to this piece over H. The cosine of this angle is also equal to this little piece over H. These angles are equivalent to each other. So I'll call this angle theta, and what does that tell us? This angle must be 180 minus theta. Sine of this angle and the sine of that angle, 180 minus theta, one in this little second triangle here, this obtuse angle, they are the same. And that's exactly what you do as you work through a law of cosine, a law of sines, and you do your double check on your angles. Remember, you always looked on your calculator, looked at this angle, you know that's a good clean triangle, and then you investigate to see if you have a possibility of a second triangle. Why? Because of the fact that the sine is positive in quadrant 1 and quadrant 2. So I hope this visual and quick explanation gives you a little bit more background behind the dynamics of the ambiguous case for the law of sines. Hopefully it's a nice way of looking at it, maybe a different way of looking at it. Again, remember, too short, just right, multiple options, one option. And one more thing, just to kind of reiterate what I do as I talk through this, I always think about a go right triangle when I have to move my connector further out to the right, or a go left triangle where I bring my connector in back to point A. Hope this helps.